In today's video, I'm going to cover concurrent collections in C#. It is going to be a little bit more detailed than normally. So the topics that we're going to cover today are understanding concurrent collections, some of the common concurrent collections that are used, race conditions, deadlocks, performance considerations, and as always, I'm going to use practical code examples to demonstrate the topics. Okay, let's start with a very basic code example right away. First, we're going to use a normal collection, in this case dictionary, and then I'm going to use concurrent collection in order to demonstrate what the difference is. But when you use a normal collection and you are working with multiple tasks or threads, you are going to use one of the several methods to avoid the common problems. In this case, we're going to use locking in order to prevent some of the problems, and I'm going to explain what is going to happen if we don't do that, and then what is the difference between using a normal collection and a concurrent collection. So let's take a look at the code example. We declare our static dictionary, and then we have a method which is called add items to normal dictionary. The method simply checks if our normal dictionary contains a key, and then it sets the key value pair. And as you can see, we use a lock, and I'm going to explain a little bit later why we do that. But first, let's step through the code. Right here, we create an array of tasks, and then each one of these tasks is actually going to schedule the add items to normal dictionary method, and this method is going to be executed asynchronously. And this is why we need to make sure that we use a lock. What is going to happen if we don't do that? Well, let's see. We get system aggregate exception, one or more errors occurred. So what does the lock do? The lock makes sure that only one thread at a time is going to execute this code. And without using the lock, if we skip that, it is likely to get either race conditions, inconsistent state of our dictionary, or exception as in this case. And what makes this problem very difficult is that each time around the program, a different outcome can be seen, which makes it very difficult to track and fix. When multiple threads access and try to modify the dictionary at the same time, the race conditions can happen, and this could actually lead to unpredictable behavior and corrupted data. Now let's modify the program to use concurrent dictionary, which is one of the concurrent collections available in C#. Then I'm going to explain what the difference is, and after that we're going to go back to race conditions, deadlocks, and I'm going to try to explain them in a little bit more detail. But first, let's use concurrent dictionary instead of normal dictionary. So I'm going to make a few changes. We're going to rename this to concurrent dictionary, and I'm going to change this to concurrent dictionary. And since this is a concurrent collection, we're not going to need this lock, this line right here. We can remove it. So let's do that. And as far as the code is concerned, this is the only difference. We remove the locking since the concurrent dictionary is optimized and can be used safely from multiple threads. So let's run the code and see if it works properly. And we get total items in concurrent dictionary 1000, and we can actually run it a few times, and every single time it is going to execute, there are going to be no exceptions. So what is the difference between using concurrent dictionary versus dictionary? As you saw, this means removing only one line of code in our case, but in general, locking can get complicated since you need to be very careful when and where to use it, and in a more complex program, it can be quite difficult to use it properly all the time. But using concurrent dictionary not only simplifies the code by removing the locks, but also reduces the risk of deadlocks, because using explicit locks, as I explained, in more complicated programs can actually lead to deadlocks if they are not used carefully and properly. And we also have improved performance since the concurrent dictionary is optimized for concurrent access, which means it is optimized for being used from multiple threads at the same time. And this leads to improved performance, and also it improves the maintainability, because simplified lock-free code is actually easier to understand and maintain. And we can, of course, simplify our code further by using the try add concurrent dictionary try add, which basically does the same. If the key already exists, this is going to simply return false, and it is not going to raise an exception. And this is going to make our code even simpler. And now let's take a look at the concepts of race condition and deadlock. As always, you can pause the screen and read the definition, occurrence, symptoms, and how to prevent them. But the main thing you need to understand is that these are two separate, distinct issues in concurrent programming, and they are not linked to each other, and the one does not cause the other. When it comes to race conditions, they happen when two or more threads access shared data and try to change it, try to modify it at the same time. On the other hand, the deadlocks happen when two or more threads are blocked forever, as each one is waiting for the other to release a resource. And as I already mentioned several times, these can be very difficult to trace because you can code your program, you can run it hundreds of times without any issues, and then once in a while a race condition or deadlock can actually happen, and it's going to be very difficult to reproduce, and it's going to be very difficult to log the error and find the cause and fix it. So make sure that you understand what they are and how to avoid them. Now let's take a look at the concurrent collections in C#. They are concurrent dictionary, concurrent queue, concurrent bag, concurrent stack, and blocking collection. We're going to start with a concurrent dictionary. We already did one simple example. This is a bit more realistic, more real life like. One very common problem that needs solving, especially in web applications, is updating a cache or user data from multiple threads. And this is what we are going to simulate here in our console application. So let's take a look at the code. We have a static concurrent dictionary. We have a user profile class with several properties: user ID, name, and age. And we have a method which is called update user profile, which takes the user ID as an input parameter. And what the method does, it updates the user profile by using the add or update method, which means that if the user does not exist, if the user with this ID does not exist, it is going to be added. If the user with this user ID exists, the name and the age are going to be updated. And again, in our main method, we create an array of tasks, and we call the update user profile method asynchronously from each one of these tasks, and we use the task wait all to wait for all of them to finish running. First, let's run the application. Actually, let me put a console read line here. Let's run the application and see the output just to make sure that everything works as it should. And you see we have updated user ID and all the threads and the user IDs and the name and the age. We can run it a few more times. And as you can see, the execution order is not guaranteed. Sometimes we're going to get the user ID with number 4 updated, and other times we run the program, the user with ID 1 is going to be updated first, and so on. You see that we have no issues updating the user profiles. Since we're using concurrent dictionary, we don't need to use explicit locking, and we can just run our code and be sure that it's going to execute properly. Later on, I'm going to go over all the collections and compare them and explain when you might want to use one over the other. In this case, using concurrent dictionary makes perfect sense because it provides thread-safe operations for adding, updating, and retrieving the key value pairs. I mean, right here we have a collection which uses the user ID as a key since they are unique, and we're using it to safely update or add our user profiles from several threads. And now let's take a look at the next concurrent collection, which is the concurrent queue. The concurrent queue is ideal for any type of producer-consumer scenario, which is also very common. And let's take a look at the code. Inside our main method, we have 2 producer tasks and 2 consumer tasks. And the producer method, you can see it right here. It simply takes a integer as a parameter. We use this integer to label the items. So this task here is going to use a producer ID 1, meaning that it's going to add items which are labeled 100 and 101, 102 up until 109, and this one here is going to use the parameter 2, which means it is going to add items which are labeled 200, 201, 203, and so on until up until 209. And then we have the consumer method. This loop is going to stop when the producers are done adding items and our queue is actually empty. So let's run the code and see how it executes. And again, the order of execution is not guaranteed as before. And you can see that we have consumer 1 processed item 200 and producer 2 added item 200 and so on and so forth until our consumer method is done and we exit this loop right here. And the main outcome from this code example is that the concurrent queue is perfect for almost any of the producer consumer scenarios that you are likely to encounter. Now let's start with the next collection, which is the concurrent bag. This is the code example that I have created. So let's take a look at the code. We have a concurrent bag, which is called results. And as the previous examples, we have an array of tasks. And again, they're going to be 10 different tasks. And what are they going to be doing? They're going to simulate some work. In this case, we're going to add integers to our concurrent bag, which is called results. And each number is calculated by multiplying the task number by 10 and adding j, where j is our variable in this loop. And we're using the wait O method, which means that the main thread is going to wait for all the tasks to complete. And then we're going to display the result to the screen, to the console. So let's run the program and see the output. And you see we have the 79. So this is the task number 7. Adding all these numbers, that we have the task number 3, adding all these numbers and so on. And as always, if I run the execution several times, the thread of execution is not guaranteed. You can see the task number 3 has executed first, then the task number 0, which is the first task in the array, has executed second, and so on. So why is the concurrent bag the collection that we want to use here? Well, there are several reasons. Again, this is a concurrent collection, which means it is thread safe and it allows our program to add to the concurrent bag from several threads without any use of explicit locking or other synchronization mechanisms. And the concurrent bag is quite performant, which is always good. And in this case, we have chosen the concurrent bag because the order in which the results are processed or retrieved doesn't matter. So this is not an ordered collection, so we don't care if the first task executes first and how the numbers are added and retrieved in what order. So this is what makes concurrent bag the right choice for this program. Now let's take a look at the next collection, which is concurrent stack. Let's take a look at the code first and then see why we chose concurrent stack for this program. First, we create our job stack, which is a concurrent stack. It holds integers. And again, we're going to use several tasks, in this case 3, to push items into the stack. And since this is a concurrent collection, we should have no problem doing that, even without using any explicit locks. And you can see that we're pushing the items right here. There's nothing really magical happen here. We again sleep for 10 milliseconds to simulate some work. And then what I'm going to do is I'm going to print the items of the stack. And finally, we're going to use a single task to pop the items out. Now I have added a few lines of code. Let me just remove this for now, and I'm going to add it back later just to show you something that is quite unique when it comes to using a stack instead of, say, a list. But let's run the program first and see what it does. Okay, first of all, we have our tasks pushing items into the stack. You can see again the order of execution is not guaranteed, and we're adding job IDs and so on and so forth. And then we're using our loop to show the items in the stack. and they are 29, 19, and so on. And you can see that the items are popped out from our stack, and they pop out in the exact same order. But you need to make sure that you understand this. When you're using for each, in our case, when using concurrent stack, this for each loop iterates the items from the top to the bottom. And this is why we're using concurrent stack when we need to have a program which fits the last in, first out scenario. If I have to simplify this, let's say we have a single task that pushes the items to the stack, and the items are 1, 2, 3, 4, 5. When we pop the items out, they should be popped out in the reverse order, meaning 5, 4, 3, 2, 1. And I can demonstrate that for each loop, in this case, prints the items from the top to the bottom by using this line of code here. If you take a look at the documentation, you're going to see that the try peak gets the top item without removing it. That means that we're going to print the items right here. Let's run the program and see what it does. Okay, you see that for each loop was 9, 29, 19, and so on. And when I get the top item from our stack, it is 9. Meaning that for each loop goes from the top to the bottom. And when we are popping out the items, again, we start from the top and we go all the way down to the bottom until we remove all the items. Just to summarize, use the concurrent stack when you need a thread safe concurrent collection and when you need a program which uses the last in, first out scenario. And now let's take a look at our last code example, which uses blocking collection, which is the last one from our list of concurrent collections in C#. And let's take a look at the code and see how it works and why choosing blocking collection makes sense in this case. So we create our blocking collection, which is going to hold integers, job IDs again, and we're going to create our producer tasks, 4 of them in our task array, and each one of them is going to add 10 job IDs. And again, we simulate work by adding a slight delay, which is 10 milliseconds here, and we're using one consumer task, which is using the getConsumingURL method to remove an item from our job queue, and we are simulating work again by using a slight delay, which is 50 milliseconds. We're using the wait all to wait for all the producer tasks to finish their job. We are using the complete adding method to signal that the producer tasks are done and the consumer task is going to complete, and we're using the consumer wait method to wait for the completion of the consumer tasks. So let's run the code first and see how it works. And you can see at the very beginning we have the producer tasks adding items, adding job IDs, and with a slight delay the consumer task has started and is processing the job IDs. When all the producers are done, only the consumer task keeps running until all the items are removed from our blocking collection. Now, why use blocking collection in this producer consumer scenario? If you remember, we could use the concurrent queue, which is also good for producer consumer scenarios, but there is a difference between the blocking collection and the concurrent queue. The blocking collection supports blocking operations, which means that the consumers can wait for items to be available and producers can wait for space when the collection is bounded. So if I have to compare the two, the concurrent queue and the blocking collection, use the concurrent queue when you need a simple non-blocking queue, which is used by multiple threads, and use the blocking collection again when you need thread safety and you need blocking and bounding capabilities. And finally, here is a very quick summary of all the collections that we covered in this video. The concurrent dictionary, concurrent queue, concurrent bag, concurrent stack, and the blocking collection. You can read the definitions and the use case. I'm not going to do that. You can pause the screen and read them and basically find out when you might want to use each one of them. And that is all from me for today. Thank you for watching.